So, good evening, friends. Today, we are going to discuss about the power of explanation and the power of prediction. So, there are two methods of doing that. One is called blind folding, and second is known as PLS predict. So, these are the important parameters of PLS SEM. So, we are going to discuss this part today. So, the four things we are going to discuss today. What is the explanatory power and what is predictive power? And if you are writing a paper on PLSM, the explanatory power is very, very much important. Predictive power we can do with the help of two things. One is called blind folding procedure, and the second method is called PLS predict procedure. Both the procedure I will show you today, and the formulae which we are going to use in today's session are these. So we will discuss one by one. So the first topic is explanatory power. Whenever we run the regression model, the most important term which everybody may ask you is what is the R square value of the regression model. So what is the value of R square? So R square is the value which explains that how much dependent variable can be explained with the help of regression model. This is the definition of R square. So it is a measure of explanatory power. Because the definition of R square is how much dependent variable can be explained. How much dependent variable can be explained. So this word explained indicates that we are going to explain the dependent variable with the help of regression model. So R square is a measure of explanatory power. It's a basic measure of explanatory power. But in R, we are also using the another term that is called F square. So we are having different terms to measure the explanatory power. But explanatory power is having one problem. So what is the problem? That the data which you are using, the data which you are using for making the model, you are calculating the R square on the same data set, right? So it is actually a problem that you are applying the regression model on a data set, and on the same data set you are defining the explanatory power. Let me explain this. This is your data, and you are calculating the value of R square. So this R square is running on this data set. Now, if you apply the model on another data 2, so and if you calculate R square, so this R square is again defining the explanatory power of the same data. So R square is basically, the problem is that R square is explaining the explanatory power of that data on which you are building the regression model. This is the problem of explanatory power. I want to know that if you make a model on this data 1, how much the model is good on data 2, right? So my question is that how much my model which is built on data 1, how much the model is good for data 2. So that is called predictive power. This is the basic difference between explanatory power and the predictive power. Explanatory power indicates the same data set, the same R square. Predictive power means a different data set, but same model. So that is the basic difference between explanatory power and the predictive power. So ability of the PLS structure model to explain the dependent variable on the basis of the different independent variable in the model is called explanatory power. And predictive power means new observations. So you can see this word, how much the model is good in the new observations. So that is called predictive power. Now, if you run SEM in MOS, you are having so many goodness of it. But in PLS, we are not having so many goodness of it. But PLS is having a very good feature that is known as predictive power. So one of the conclusions that I want to write here, that the MOS is having goodness of fit indicators, and PLS is having predictive measures. So this is the basic difference between PLS and MOS. MOS do not have the predictive measures, and PLS don't have the goodness of fit indicators. So this problem of MOS is solved by PLS by providing you the predictive measures. And these predictive measures, and we are having three predictive measures, FSquare and Q square. There are two types of Q square, small Q square and capital Q square. So we are having these three new things in the PLS, which is measuring the predictive power. So these are the new things that we are going to learn today. So I hope you understand what is the difference between explanatory power and predictive power. Predictive power means if you run the model on the new observations, how much accuracy we are getting in the prediction of dependent variable. Okay. Now, in another language, we define this term explanatory power and predictive power by using in sample prediction and out of the sample prediction. In sample prediction means you are using the same data for predicting the dependent variable. That is called explanatory power. If you use other observations to predict the dependent variable, this is called prediction power. So explanatory power is called in sample prediction, and predictive power is known as out of the sample prediction. So these two terms we can also use. And if you have any query, you can put in the chat box. I will also see that. So basically, we are comparing the explanatory power and the predictive power. So there are new terms which we introduce in the PLS. One is called FSquare and small Q square and capital Q square. So these are the new things which PLS is providing to us. Now we are having two terms, R square and F square. Both are the measurement of in sample prediction means explanatory power. And out of the sample prediction means we are applying the same model on other data set and calculate how much is the prediction accuracy. Prediction accuracy is measured by two things, capital Q square, small q square, and also PLS predict. Okay, now I will explain you each and every term in detail. Okay, why predictive relevance? Actually, we are living in the era of machine learning where you run the model on one data set, validate the data on another data set. Actually, there are three types of data set I'm telling you. Let me explain this term in another window. We are having basically we are dividing the models into two categories: supervised models and unsupervised models. Similarly, type of data, we are having three types of data. One is called test data, then train data, and third is hold out data. Why I'm telling you these things? Because if you use these terms in the research paper, it will add value. Okay. Now, let me explain what is the difference between supervised and unsupervised. In supervised, you are having output variable, input variable. And in unsupervised, we don't have output variable, only input variable. So in supervised models, we are having dependent variable y and some independent variable x1, x2, x3, and so on. In unsupervised models, we are having only x1, x2, x3, and so on. So in this term, in this case, the SEM PLS is our supervised model, because in SEM PLS, we are having dependent variable as well as independent variables. So I have seen many papers where they compare the PLS with other supervised models like neural network. Recently, I found a paper where the comparison is done between PLS and neural network, and they prove that the PLS is much better than neural network. So if you think in that way, you can give new dimensions to your paper. New dimension means you are saying that the comparative analysis of the model with respect to PLS and neural network. So you can go to other supervised model also. So there are many other supervised models. So now I have seen some of the researchers are moving in this direction. They are comparing the PLS model with other supervised models such as neural network. And if you want, I can also compare this topic in this workshop, how to compare PLS model with the other supervised model. That depends upon your interest. Okay. Now, other thing is that data. So we are having three type of data set: test data, train data, and holdout data. Now, what is the meaning of this, the data? So listen carefully. Normally, we are having only one data set in the beginning. So we are having one data set, single data set in the beginning. And this data set is divided into three parts. So this is the 70% or 60% of the data set. So we run the model on this data set. This is called test data. Test data is the data on which you are running the model. Then you are, it is a train data set. Train data set is the data set where you run the model. Then you have test data set, which is 30%. And in this data set, you are examining the accuracy. And in third case, you are having the holdout data. This data is also coming from the main data set. From the main data set, you are having 10% of the data, and you run the model on 10% of the data and check the accuracy. So this accuracy is telling you how much your model is having the predictive power. So we are having this kind of system. I have seen in the papers, they are dividing the data into 6:3:1 ratio. They run the model on 1, check the accuracy on test. If fine, then they go for second validation. So this stage is called validation of the data. So this thing we have to perform. Now, one more thing. Whenever I say the accuracy, so the accuracy is measured by Q square, capital Q square, and then RMSE. In some softwares, we also calculate entropy. Now, these three values we are getting from the PLS. The softwares like neural network also give you the value of entropy. Entropy means confusion. So high confusion is always bad, low confusion is always good. So lower the value of entropy, you are having the best result. Okay, so the power of SMART PLS is that it will gives you these values so that you can examine the predictive power. So I hope now you are having the idea of why we are preferring the predictive power for PLS. And nowadays, I have seen the scholars are doing research on carbon finance, environment science, supply chain, big data, the machine learning. So all these topics are new topics. Theory is not there in the literature. So they are preferring the PLS software for testing of the model and the validation of the model. So this is a new area, and I have seen that their papers are published in A category journals. So in this direction, you can also think. And they are also doing one thing. They are comparing their PLS model with other supervised models like neural network. So I hope you have idea about that. So come back to the PPT, and I hope you are having now the knowledge of predictive relevance. So why predictive relevance is important? For high level of generalizability of the conclusions, you can say that if my conclusions are valid in sample, it must also be valid in out of the sample. And explanatory power, because whole MOS models, regression models, are based on explanatory power. You have to report the R square value, but in PLS, the explanatory power is not sufficient. You have to apply predictive power also. So that is the advantage of PLS software. Okay, sometimes what happens then, if you run the model in sample, the explanatory power is good. When you apply the same model on any other sample, your R square drop down. So the reason is that your sample is very small as compared to population. Most of the observations lie outside. Your sample is hardly 1% of the data set of the population. 90% of the observations are outside. So you have to prove that your model is having good predictive relevance. Okay, so for this is for external validity, and it is a standardized practice in machine learning and artificial intelligence. Whenever you make a model, you have to test the validation of the model. It is a standard practice. So nowadays, it is a standard practice for finalizing the estimated model. We have to check the external validity of the model, which is known as predictive relevance. So I hope you have now understanding of the predictive relevance. How we are doing it, I will show it. So I will show you how to do all these things. Now, first of all, I will explain you the new terms in explanatory power. Then I will move to the predictive power. So there are three measures of explanatory power. One is called R square, adjusted R square, F square. So these are the three terms which we have to explain. R square, adjusted R square are very common because most of you, if you applied regression in your life, you must know what is R square and adjusted R square. But F square is something very new, right? So that I am going to explain. Okay. Now, what is the difference between F square and R square? So this you must know. The basic difference of R square and adjusted R square is that they are calculated for dependent variable. These two terms are calculated for dependent variable. But do you know the F square is calculated for independent variable? So this is the basic difference between R square and F square. The R square, adjusted R square, calculated for dependent variable, and F square is calculated for independent variable. So how we do that? Let me explain. So the first concept is R square. Whenever you run a model, whether it is a regression model, whether it is a PLS model, MO software, the panel always asks you that what is the explanatory power of the model. Tell me your R square. And I have seen that you say that R square is 40%. The panel members say that your R square is very low, we are not accepting your model. So then a researcher try to find out the literature that what is the average R square I'm getting in my results. And one more thing that I'm telling you, the R square depends upon the effect size. Effect size means if your model have more effect size is measured by beta correlation. If you have high path coefficient, you have more R square. If you have low effect size, you have low R square. So R square depends upon the path coefficient you are getting from the results. And I have also seen the cases that a research scholar come to me and told to me that, sir, my R square is very high. It is rejected by the panel member. Panel members say that in your area, R square of more than 50% is not possible. So your R square should not exceed 30%, 20%. So both type of problems are there in the literature. In psychology, R square more than 25% is very low. In finance, R square even more than 5% is very rare. But in social science, like in marketing, the R square is expected to be more than 50%. In medical science, even you must have the R square more than 80%, 70%. So there are many areas where R square are standardized. So R square is the basic thing which measures the explanatory power. It represents how much variance in dependent variable explained by all independent variable. And it is normally, right, irrespective of the finance, marketing, psychology, if R square is near to the 25%, it is weak power. More than 50% moderate power, and more than 75% is substantial power. The R square, there are two methods of increasing the R square. I'm telling you, as a statistician, I'm just going to tell you that there are two secrets of measuring the R square. Number one, by adding more number of variables, you can improve the R square, or by removing the outliers. If you remove 5% of the outliers, you can improve your R square. So in PLS, sometimes we cannot add the new variables, but we can identify the outliers. So if we have the facility of finding out the outliers, we can improve the R square of the model. So this is one of the possibility that how we can improve the R square. And the second technique, that how to identify the outliers, I will also show you. Not today, but some other day. Okay, now this is the R square, but R square is having one property. Whenever you add a new variable, it always increases. So whenever you add add a new variable, whenever you add a new independent variable, the R square of the model always increases. So sometimes it is not good, because you cannot increase the model by many independent variables. So in that case, you use the adjusted R square. Adjusted R square is the R square adjusted by the degree of freedom. So now we are having a new measure, adjusted R square. What is the role of adjusted R square? The role of adjusted R square is that when you add a new variable in the model, if adjusted R square also increases, then the variable is good for the model. And when the adjusted R square is not increasing by adding a new variable, then the new variable is not good. Let me explain you like in this way. Suppose you are having x1, x2, x3, and they are influencing the y, right? And you want to add x4. So you run another model, x1, x2, x3, x4. So you are having the model 1, you are having the model 2, and if we have R square and adjusted R square, if R square is 40%, suppose it is 40% and it is 41%, on the basis of R square, you are saying that the model 2 is good, because R square always increases. If you add a new variable in the model, R square always increases. But adjusted R square, suppose it is 39% and it is 38%. So if you compare the adjusted R square, you are saying that the adjusted R square of second model is low. So there is a confusion that which model is good. This is low and this is high. So R square is increasing here and R square is decreasing here. So finally, we have to check the adjusted R square. By looking at the adjusted R square, you have to decide whether my model 1 is good, whether my model 2 is good. So whenever we compare these two models, we always check their adjusted R square to finalize that which model is good. So in this case, we go for model number 1 according to the adjusted R square. This is the final conclusion that we can draw. So this is the importance of adjusted R square. So in your paper, you can report both R square and as well as adjusted R square, but adjusted R square is more important when you compare two different models. Right. So if you are comparing two different models or three models, then you can use adjusted R square. But if you are having only a single model, then R square is sufficient. So this is the difference between R square and adjusted R square. So I hope it is clear. If it is not clear, please write in the chat box so that I can explain another way. Okay. So no queries coming, it means it is clear. So we have two measures of explanatory power. One is called R square and second called adjusted R square. Now I'm telling you what is F square. So F square is a measure of effect size. We are using the word called effect size. And effect size is always calculated between the dependent and independent variable. Okay, let me explain the F square by another way. First of all, listen this example. Okay, we are having x1, x2, x3, three variables, and these three variables are impacting the y. Now, if I ask you, what is the explanatory power? What is the explanatory power of y? You can tell me the value of R square. Now, if I ask you, what is the explanatory power of x1, x2, x3? What is the explanatory power of these three? So you cannot express by R square. You will calculate the f1 square of x, f2 square of x2, f3 square of x3. So there are three F square, and you are calculating the F square for each independent variable. So now you know that F square is always calculated for independent variable. This is one thing you should know. The second thing is that how we calculate the F square. Now let me explain the methodology, how we calculate the F square. And it is very simple. I'm telling you. Suppose we want to calculate the F square of x1. So we will run another model like x2 and x3. So this is model 1. This is model 2. You measure the R square of model 1 and you measure the R square of model 2. So this is called R square included, R square excluded. In first model, x1 is there. In second model, x1 is not there. So we call it R square included, R square excluded. One thing is very clear, that R excluded is always less than R square included, because you are removing one of the variable, and because of that variable, the R square excluded is always less than R square included. Now the question is that how much they are less, how much R1 square is more than R2 square, RE square, how much is the difference? So this difference, we have to make some standardized formula for calculating that. So what we apply R square included minus R square excluded upon 1 minus R square included. So this is the formula for F square. And F square is calculated simply from this difference. If this difference is more, it means F square is high. If this difference is less, F square is less. So if we apply this formula, we can calculate the F square, and we are having three ranges of F square: 0 to 0 point, or let's say 2%, 2% to 15%, 15% to 35%, and more than that. If F square lies in this range, it means zero effect size. So we call it zero effect size. If you have F square in this range, you call it low effect size. If F square comes in this range, you call it moderate effect size. And if F square comes in this is called strong effect size. A strong effect size. So in this way, we calculate the importance of F square. So let me explain the PPT. Now see carefully. The formula is written here. The F square is equal to R square included minus R square excluded, 1 minus R square included. So, and F square is having three rule of thumb. If F square is more than 2% but less than 15% is weak power, F square more than 15% but less than 35% moderate, and F square more than 35% is substantial. Actually, in one model, you don't have only one independent variable. So most of the time you are having many independent variables. For example, you are having x1, x2, x3, and F square is 2%, 10%, and 40%. So you will get the different values of F square of different variable. Now you can say the effect size of the third variable is very high, strong effect size, moderate effect size, or low effect size, and no effect size. So you can tell that x3 is the most important variable which explains y in the regression model. So in this way, we can explain the effect size of independent variables. And believe me, whenever you are writing the paper based on SMART PLS, F square is the value which you have to report in the paper. So that is the value of F square. Now from my side, the explanatory power is done. Let me show you the value of F square first, so that you can have idea how we can run the F square. So I'm running the same model which we are running from last 2 days, and I'm showing you how we can calculate the F square. And today we are going to do the PLS model. This is our exercise number 1, and this is the model. When we run the model, we are getting the model. In this is the simplest model where we are having one independent variable and 4 independent variables. I am going to examine the values, how much they are influencing the Y. This is my model. So I go to the calculate, go to bootstrapping, because now my objective is hypothesis testing, not uh, the assumption testing. So I go for bootstrapping. Number of bootstrap, normally I'm taking 500, but it will take more time. So I'm decreasing bootstrap time. If I run basic bootstrapping, I will not get the value of F square. I will get the value of F square only when I go for complete bootstrapping. So you run this, and the software will give you the results. Now let's see the result. This is known as inner model, you know very well. So I can increase the path coefficient so that you can see it clearly. This is my path coefficient, and the software is showing you the t statistic. Okay, I want to see the I don't want to see the path coefficient. I want to see the p value and path coefficient, not t statistic. So I go to inner model. So you can see that I have this option. So you can see I have this option inner model. In this option, I click on this part and click on the path coefficient and p value. I want to see the path coefficient and p value. So now I am getting the path coefficient and p value. Path coefficient is found to be highest. In this case, this is number 1, and this is number 2, and then this is number 3, and this is number 4. And all the path coefficients are significant because the p value is less than 0.05. Right. So I have the idea that the effect size of this is highest, second highest, third highest, and the fourth highest. But just by path coefficient, it is not sufficient. I have to show with the help of F square. So how to check the F square? You just go for bootstrapping and you get the value of F square. You can see that the R square, adjusted R square, F square, you are getting it. So now I just want to show you F square. So F square, you can see there. This is the value of F square. F square is more than 2% in every case, but it is not very high. So in all the 4 cases, the F square is lie between 2% and 15%. So what I will make remark here, the low effect size, low effect size, low effect size, low effect size. So I will put this remark in the paper that although all the independent variables are significantly influencing dependent variable, but effect size of independent variable are low. So this is the remark you have to put. And second thing, I am showing you the explanatory power by R square. The R square is only 51%. The R square is only 51%. So you have to report the R square as well as the F square. The way you have to report it, you have to make the table. This is independent variable, path coefficient, t statistic, p value, R square, F square. So in this table, you have to report that low, 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 low. R square is 51%. And if R square is 51%, we can say it is a moderate explanatory power. So this is my suggestion to you. Whenever you apply the PLS model, you have to report the R square as well as you have to report the F square. F square, by F square, you are representing the effect size of the independent variable. How much is the effect size of independent variable? I think now you have clarity on the F square. What is the meaning of F square? How we interpret the F square? So very simple. So now I have demonstrated you that for a PLS model, how we can calculate the F square of independent variable. And remember that F square is always calculated for independent variable and R square is calculated for dependent variable. So you can see the value of R square here. Okay. Now let's move to the PPT. So from my side, the meaning of F square is done. Okay. This is the value of F square. And there are 2 types of F square. Let me explain. If you see, there are 2 types of F square. One is original sample and second is the sample mean. Now, what is the difference I'm telling you? This F square is without bootstrapping procedure. This is called original means without bootstrapping. And this FSquare is with bootstrapping. So there are two FSquare, and don't confuse with any other term. So more or less both are same. Only thing is that there is a slight difference between the FSquare, like 3337, 5361. You will have different value of FSquare, but the difference is not much. So don't confuse with it. It is always better to go for bootstrap or FSquare, because software calculate FSquare for different samples, take the mean of that. So that is called with bootstrap. I hope it is clear. And other things are not very important. Okay, so we take only from there. Let's move to the PPT. I hope it is clear now. Abhijit is asking why p-values are different. Which p-values you are talking about? Because we are having only one p-values. P-value. This is the p-value of one independent variable. This is the p-value of this independent variable. So we are having the different p-values for different independent variables, right? And these p-values are indicating that the FSquare values are very low. So we are having the low effect size. But if we go for the path coefficient, you can see this. In path coefficient, p-values are significant. It indicates all the independent variable have a significant impact on dependent variable. But if you go to the FSquare, the p-value are representing that the effect size are low. So this is the difference between FSquare and R-square and path coefficient. So I hope it is clear now. Now the question is that you are asking that what we can do with when FSquare is low. So this is most of the people are asking question what we can do if FSquare is low. So if FSquare is found to be low, the only solution you have is to remove the outlier from it. You can find out the outliers from the model, and by removing the outliers, you can remove. After removing the outliers, you can improve your FSquare value. So removing the outlier is only one solution, and the outlier you can find out the from POS. So this is the prediction orientation segmentation. So this is the method, one of the method provided by the PLS, by which you can find out the observations where the FSquare is very low. If you remove those observations, in the rest of the observations, you are getting the high value of FSquare. So that's very easy, believe me. So whenever I will teach you this POS, I will also tell you that how we can find out the outliers where the if we remove these outliers, the model will be improved. You can improve the model, but that is a separate different topic. So I'm not covering this POS today. Let me continue this topic. So today I'm covering this blindfolding and PLS predict. So these two techniques I'm covering today, PLS predict and blindfolding. Okay, so let's move to the PPT. Now, after understanding the importance of explanatory power, now we have to understand the importance of predictive power. So